So you certainly can look up the pKa of all your functional groups, but remember that that big idea of this class is that structure determines function. And so you should be able to look at the structure of a molecule and determine both which proton in the molecule is most acidic and do a kind of a relative ranking of acidities of various different compounds just by looking at their structures and not looking up the pKa. So the reason that we can do this is because the more stable the conjugate base, the more acidic the acid. And we can look at a compound and make some judgments about the relative stability of the conjugate base. So for instance, if we compare butane and propanol, we would then write the conjugate base of each of these compounds, where butane would lose a proton, donate a proton as an acid, and propanol would also do that. And so we wind up with the conjugate bases shown below the two compounds. And when a negative charge is on a more electronegative element, that's more stable than when it's on a less electronegative element. And so this would be the more stable conjugate base, which means that propanol is the most acidic proton. So there's actually 4 different aspects of structures that contribute to the conjugate base stability. The one we were just looking at is the element effects, and that's the effect of the identity of the atom to which that acidic proton is directly bonded, not bonded somewhere down the line or somewhere else on the molecule. We're really looking at the protons that are directly bonded to the element. Hybridization effects, resonance, and inductive effects, and we'll just look at these each briefly here. So element effects are by far the most important effect. And so if you look at this table where we have kind of a number line of pKa's, but do remember that those are logs, right? And so pKa of 50 is much. It's 10 to the minus, or it's 10 to the 50 times more acidic than something on this side of the table. So that's a lot. So increasing acidity is from right to left on this table, and you can see that when you have an oxygen that your proton is directly bonded to, then the compound is much more acidic than when you have a carbon, a less electronegative element that the proton is directly bonded to, like with ethane or acetylene here. So this is because of that relative electronegativity and also some relative size effects when you go down the table. So atoms that are more electronegative are going to be better able to hold that negative charge. They're more stable with a negative charge. And so their conjugate acids, if you can see here, are more acidic. So the proton is easier to donate. It results in that more stable conjugate base. Size is also significant in considering the stability of the conjugate base. And so as we go down the table, the size of the ions gets larger, they're more polarizable, and so their conjugate bases are more stable because that negative charge can be better shared or spread out. And so the conjugate acids, as shown in the bottom table, are more acidic. So hybridization is second in the table, and the more S character that you have in a hybrid orbital, and actually Klein calls this the orbital effects, but the more S character you have in a hybrid orbital, the more stable the negative charge is because it's closer to the protons of the atom. And so sp is 50% S because there's only 2 orbitals that kind of get averaged together. to give you an sp orbital. So s is half of that. So it's 50% s character. Similarly, for sp2, it's 33% s character, and for sp3, s is 25% s character. And so, so that sp is more stable. The negative charge is closer to the positive because s orbitals are closer to the positive charge than p orbitals are. And so you get increasing stability from left to right here, and then increasing acidity of the acid as well. So both the element effects and the hybridization effects or orbital effects involve protons that are directly bonded to the electronegative element. So it's also the ability to spread out and share charge in the conjugate base, that should say conjugate base, is also important. And resonance effects and inductive effects talk about sort of charge delocalization in various different ways. So if we compare ethanol and acetic acid, the question would be, well, which is more acidic and why? And in both cases, it's the proton that's directly bonded to the oxygen that's going to be most acidic. It's the question of, well, which one of those between the two is actually more acidic. And so the first thing that you always do is draw the conjugate bases to compare. And so we end up with ethoxide and the carboxylate over here. We have the negative charge directly bonded to or directly on the oxygen in both cases. Right, so then we can see if either of these structures could be stabilized by resonance, and the carboxylate can be. It has that pi bond that's next to the negative charge over here on this oxygen, and so we can draw a resonance structure that shows that the negative charge is actually being shared by two oxygens. So that negative charge is delocalized, it's spread out, which makes it more stable. It's like if multiple people were trying to carry a weight, it's more stable when multiple people do that rather than one person doing it. So, so this conjugate base of the ethoxide is going to be less stable. This one is more stable, which means that acetic acid is more acidic than ethanol. And indeed, if you went back and looked at the pKa's, you would see that the pKa of acetic acid is, around 5, whereas ethanol is around 16. Finally, we have inductive effects, and this is where you have electronegative elements that are stabilizing the conjugate bases that aren't directly bonded to the proton that is acidic. And so, for instance, look over here at this R group. Okay, so in this case, the proton that's directly of the carboxylic acid is the one that's being donated to water. It's the acidic proton. What's changing is this R group. And what you can see is that the more electronegative elements you have, for instance, CF3, that's the most acidic R group, or most acidic substituent on this molecule. It leads to the most acidic carboxylic acid. And then if you have fewer of those, like CH2F, you can see that it's still more acidic than just having a CH3 group, but it's not as acidic as when you have more of the fluorines. And then when your electronegative element is further away, it also has less of an ability to spread out the charge, delocalize the charge through sigma bonds, which is what we call an inductive effect.